Hey guys, it's going to be a video about free fall. Alright, Aristotle and Galileo were the scientists talking about free fall. Well, most of the scientists were talking about, but those two made the two claims about free fall. And Aristotle said heavier objects fall faster. And he lived around like 384 and 322 before BC. So that was a really early observation that Aristotle made, and it was accepted at that time. And after that, Galileo came after like 800 years later, and then he said every object falls with the same rate regardless of their mass. So it doesn't matter what the size, what the mass is, every object is going to fall with the same rate. So the reason that objects fall with different rates is air resistance. And since we have air resistance at Earth, we might see different scenarios. So, but at the end, we found that Galileo was right. So in a vacuum, when there's no air resistance, all objects falls with the same rate regardless of their mass, shape, and size. Alright, and that rate that they fall to the Earth is known as gravitational acceleration. So near the surface of Earth, all objects experience approximately the same acceleration due to gravity. So gravity pulls things down, and that means it's going to speed up every second. And how much they speed up? Originally, they speed up by 9.8 meters per second every second. So that's why acceleration due to gravity at Earth is known as 9.8 meters per second square. And in this PowerPoint, I'll be using 10 for gravity, but in your calculations, you're going to be using the original number as 9.8. And acceleration due to gravity is known as gravitational acceleration, and is shown by lowercase g. Gravitational acceleration depends on the distance from the center of the Earth. So as distance increases, g decreases. So that's why you're going to have a little bit thinking about the shape of the Earth and the equator. You're going to have a little bit larger distance than the poles. So your gravity, since you're closer to the center of the Earth at the poles, you're going to have a higher gravitational pull than the equator, so you're going to weigh more at the poles. All right, free fall. The definition for free fall: any motion of anybody where gravity is the only force. We didn't talk about force yet, but only thing that is pulling or pushing on the object is gravity. If that's the case, then we are considering that as free-falling object. So what are the cases for that? You basically have three cases. So you can just drop an object. So once you drop an object, basically gravity pulls it down. So that's a free fall. Even if you throw the object down, so we don't care about the initial part. So yes, we are applying some force, but after the object leaves the hand, it's still going to be falling with the effect of gravity only. So that's why not considering that initial push, the rest of the motion is still free-falling object. Or the third case, once you throw the object up, again, not considering what's happening down here, when the object is in the air, it's only going to be pulled by gravity all the time. So that object is also known as free-falling object. Alright, object drop from rest. So for those, we had for kinematics equation as delta x v initial t plus 1/2 at squared, v final equals v initial plus at, v final square equals v initial square plus 2a delta x, and then delta x equals t over 2, or there are different variations for this part, but v initial plus v final. So those four equations, these are still valid equations, and depending on the case, we're going to have certain numbers for some of the variables in those equations, and we can rewrite those equations. For example, if you drop an object from certain height, so your displacement for this case is going to be replaced with h. And since you are dropping from rest, your initial velocity is 0, then it's going to be 1/2. Your acceleration for all free-falling object is g, so it is 1/2 gt squared. So your basically equation, it's not a new equation, it's just writing the equation with the given variables. Then you basically have that simpler version of the kinematic equation. So height equals 1/2 gt squared. So considering that h, you're displacing downwards, so your h is negative, and acceleration is also downward, so that's also negative, then those negatives basically cancel each other out, so h equals 1/2 gt squared. And if we take g as 10 to like simpler calculations, then you can simply say height equals 5t squared. All right. And as object falls down, velocity increases by 10 meters per second every second, or to be more specific or like exact, 9.8 meters per second. All right, graphs of objects drop from rest. So since we are starting from certain height, and as time goes on, what is going to happen? We are going to go faster and faster and faster. So we are basically traveling some distance initially, but as time goes on, we are basically traveling more and more with the same time intervals. So you are basically going to have that graph. But our velocity is going to be constantly increasing, but it is going to start from 0 and it's going down, so it's a negative, but it is going to be increasing numerically. And your acceleration is always, always, always negative g for all free-falling cases. All right, so if you would like to have an example, I'm not going to be solving the questions, but you're going to have the solutions over here, so you can just stop and try to solve those questions, and you will see the solutions over here. All right, so you basically they give you the height and they give you the time, so you use basically the height 1/2 gt squared. And same idea, using the kinematics equations with the given variables, you can also find the final velocity of it. All right, objects thrown downward. So in this case, you are still going down, but you are going to have initial velocity greater than 0. So in this case, you are still going down and you're displacing the distance of h. So your displacement is going to be negative h. Your velocity will increase by 10 meters per second, or 9.8, and your acceleration is still negative 10, and there is no simple or simplified versions of the equations, just like free-falling objects but with initial non-zero velocity. So in this case, your height is going to start the same, but you're going to actually travel a little bit faster at the beginning. So you're not going to start from 0. So your velocity, you don't start from 0, but you're still going down and down more and more. So you're going to have more negative velocity, but your acceleration is still negative g. And again, you can stop and read, and you will see the explanation of the question over here. Object thrown upward. So in this case, what's going to happen? You're going to start from one point, and then you're going to end up at the same point. So that's why. But before we get there, what's going to happen? You're going to start with some velocity, and as you go up, you're going to slow down because your gravity, Earth is pulling you down all the time. So once you're going against that gravity, then your velocity will be going less and less. And the amount that it's going to decrease is, again, the gravitational acceleration. So it's 9.8 or 10 meters per second every second as it's moving upward. And its velocity is 0 at the highest point. So once you reach to the highest point, what's going to happen? You're going to stop momentarily, and after that, you're going to be basically going in the same direction with the gravitational acceleration. So this time you're going to start to speed up, and it reaches to its maximum height when time is half time of the total flight time. So it's basically the midway, so it's the half time. And as it's going down, its velocity is increasing this time by 10 or 9.8. And the acceleration is negative 10 meters per second throughout the motion. All right, this is important. That includes that peak point, because you might think, well, it stopped, so acceleration is 0. No, acceleration is caused by the gravity. So if you say gravity is 0 when it reaches to the highest point, then you will see that it's not meaningful. So your acceleration is always there, and the reason for that is gravity. So gravity never disappears, it's always there. So your gravitational acceleration is always going to be negative 10 or negative 9.8. And your displacement, since you start from one point and end up at the same point, your displacement is 0. So your initial velocity is going to be equal to the final velocity, but one is going up, the other is going down, so it's going to be negative. And t up equals t down. So if you know how much it takes for it to reach to the highest point, then you will be able to basically figure out the total time by just multiplying by 2. And another thing, v up is equal to negative v down, which is at the same elevation. So let's say you are basically looking at this point, and then you have some v at this point. And then if you look at the object at the same point when it's going down, it is also going to have velocity v. So at the same height, it doesn't matter which height that you pick, you can just pick any height that you want, but on the way up and on the way down, they're going to have basically exact same motion. It's the exact same replica, basically. When it's going up and down, the only difference is the direction. And when we are thinking about the graphs, this time we're going to start from 0. As we go up, we're going to slow down, slow down, slow down, reach to the maximum height, and after this point I will start to speed up, but I am going to come back to 0 location again. And my velocity time, I'm going to start with some initial velocity, and then it is going to be positive because I was going up initially, but as I go up, my velocity is going to slow down, slow down, slow down, and at the half time, it is going to stop. And after that, it will start to speed up in the negative direction, so it's going to reach to the same final velocity with the initial velocity that it has. So that's the graph for falling objects, or objects thrown upward. And acceleration time is again the same. Your acceleration is always negative g for free-falling objects, regardless of the type of the motion. And again, you can read the question and answer the question. Alright, object thrown upward from a cliff. So you don't necessarily need to go from ground to ground all the time, or the same elevation. So what you can have, you can start from above the ground, or you can start from a lower point, and then you might actually go up to a higher point like this. Same idea. You don't have any special equation for those. You just use the kinematics equation, and you just need to know some basics, basically the principles or properties of that motion. So again, same elevation. You see, this is the same elevation. So at this point, v initial is equal to negative v initial, but it doesn't stop there. So it's keep moving. So you're going to have a v final that is larger than your initial velocity. And since the time to go up is less or shorter, then your t up is going to be less than your t down. And idea is the same. When you're going up, you're slowing down by 10 meters per second. When you're going down, you're speeding up by 10 meters per second. And at the highest point, you again reach to 0 meters per second. But what's your acceleration at this point? It is, again, throughout the motion, your acceleration is always gravitational acceleration, which is negative 9.8 or negative 10 for simpler calculations. And V up is equal to V down at the same elevation, so we talked about that over here. All right, how's it going to look like? So you're going to start from some height, you're going to slow down, stop, and then speed up, but you're going to travel more, so that is basically your displacement. And for velocity time graph, you are going to reach to your zero velocity earlier, so this portion is going to be shorter than this portion. Alright, but your acceleration time is still the same. And again, you can look at this final example and the solution, and this is basically it for free falling objects.